in much. I'll leave the platform to our host for today, Charles Clark Dankwa. But before I do that, some house rules. Um, we would allow Clark to do his presentations, and then once he's done, we'll pause for some questions halfway through. If there are no questions, he continues with his presentation, and then at the end, we go on with other questions. Your co-host for today is Derek, Edem, Soso, and Obed. So without spending too much time, Clark, the floor is yours.
Right, thank you very much for the introduction. So I'm just gonna share my screen so that we start the section. Right, so let me know if you can see my screen.
Yes, Clark, your screen is visible.
Okay. All right. Thank you very much for having me, Kwame and other cohorts. We've been in the like in the training. So thank you very much for this opportunity to also present and share my knowledge about FPGAs. And I would also appreciate my colleagues as well, Obed, Hack, and then or the like other team as well. So today I just want to touch down about exploring modern FPGAs. So from the logic gate to the application. But then before that, I just want to introduce myself first, then we will just dive deeper. So as I said, good afternoon once again from wherever that you are just like listen to me from. So here it's like it's an afternoon. So my name is Charles Clark Dankwa, and then I'm a doctoral student in the electrical and computer science here in Morgan State University. I'm also a graduate research assistant as well in the National Transportation Center, which is a cyber lab, a USDOT university. So my work basically focuses on hardware development, FPGA-based acceleration, and edge computing. I also combine it with like connected and autonomous vehicles. I do V2X like communication, so like vehicle to pedestrian, like vehicle to everything communication. So I also work to help with like pedestrian safety and then also work zone safety. So tonight I will just share with you the basics of logic gates, all the way to how FPGAs are powering AI, autonomous systems, and then edge computing. So this is just a brief like an overview or just like a big picture. I will just throw a little light about what FPGAs are, where they came from, and why they are like becoming such a foundational technology. So where do this like name or even an acronym even comes from? So FPGAs is just like a field programmable gate array. So before that, there was an issue. So if I say issue, it doesn't mean that there was like a problem that needs to be solved. So engineers had like two options, and like neither of these options were great. So they had the first option was just like a fixed like functional TTL chip, which was totally like rigid. So they were just looking for a way to change the physical or like rewire the board to meet like a particular like target. So they also had like a PAL like devices, which is just like a program, like which is also just like a programmable like devices. So for those ones, they can be configured, but then once it is being like programmed, you cannot like change them or like just like alter them at the end. So we had which brought us to what's to the term ASIC. So ASIC is just like an application specific. So once you like configure it or once you tape out, you cannot make any like configurations within the hardware in itself. So like they spend like millions of dollars of years of like development just to like get the first chip, which can be easily be reconfigured. So there was this gap in the industry, and these two guys, Ross Freeman and then Bernard von der Schmidt, so they proposed something that sounded almost like quite like contradictory. So the chip was just able to be reprogrammed like repeatedly, so like without touching the entire like physical silicon. So their company, they formed the Xilinx, um which right now we have it's being like sponsored by AMD or being like purchased a AMD. So like Xilinx introduced the first chip, which is the XC2 like 2064 chip. So for the first time, they had like a hardware that can be reconfigured and which can also be um, rewired in the circuit. So this like just having this story in mind, we will just zoom out a bit and look at how the FPGA landscape has like evolved over the years, like the vendors, the hardware, and then the architecture itself. So like um like just to like talk about what a FPGA is. I think I've just mentioned an FPGA, but then if you are new here, you might not know even what I'm talking about. But then I just have to give you a simple definition. So an a FPGA is just like an IC. So that IC is you can like basically reprogram it after it has been manufactured by the like manufacturer. So if you have an IC which like the hardware can actually be reconfigured, and this reconfiguration can be done like using a hardware like description language, which can be either like a VH like DL or like a Verilog. So those are like the two programmable languages that we normally use. And the key advantage about this is if you have like your device or like your circuits, just as I said, which after you've like tape out, you cannot do any reconfiguration. FPGAs actually helps you to do that. So as I said, the key advantage is just to help you like design a logic circuit. So once you download that circuit to the FPGA board and then you discover a mistake, you can simply like go back and then make changes and then reprogram it to make like a new hardware. So we have two most important like vendors in the market. Oh, sorry, two most important vendors in the market. So the ones that we have is AMD and then Intel. So there are other FPGA companies, which is like a Finis, which they came not long ago. We also have a Artis. We have like other Digilens as well. So they are like some of the vendors that produces this FPGA boards. So like going back, this is just like how FPGAs looks like in the 19s to the 20s, and it has evolved over the years, and we would see some new ones that have been released like in the market. So this is just like how it was. So at first we just had like the PL, which we'll talk about. Like we just had like the pure logic. So we couldn't like combine it to any ARM like processor or like any processor. So it was just like a pure logic. Then over time, it's just evolved to like having some kind of like DPS like controls being added to it, like the power IC, some input and then output was like also added to uh, the chip. So it was more or less like an upgrade of where we are coming from till now. So like right now we have the Ultra Scale Plus and then the Versals as well, which combines with other like processing systems. So these are the chips. Okay. Just to run through, this is just like how it has evolved over the years. So these are new chips that sorry, not new chips, but then they are more like the modern FPGA board. So you can see when you compare it to the old ones, these are some of the like modern FPGA boards. So this is a pink board, and this is also a ZCU board, 103, yes, board, and then this is also the CRA SOM, which is currently being released by Xilinx. So this brings us to the actual circuits or the actual chip. So you can't talk about like FPGAs without like talking about the chip itself. So this is the zinc chip, and it is part of the zinc of the Xilinx zinc like family. So what makes this chip like different from like what makes it different? It's not just it being it's not just being the FPGA fabric or the PL, but then it combines with the processing system, which is the PS. So the PS is more or less like a CPU. So you can talk to this like CPU using this like buses, and these are the AXI protocols or the like the communication protocols that you can talk to from the PL, and then you can also talk to from the PS. So like instead of just like choosing either a processing system or a FPGA, you can basically like couple the two of them together, and then you can use it in your like project. So going deeper, we zoom out into how this looks like. So if you move like to the next step, and then like we just want to go into how the chip like basically looks like. This is just like the modern ones that we have like in the market. So it is just the modern FPGAs which has like evolved far beyond a simple like PL chip. So on the left side is just so the two of them are just like the Xilinx device that like basically represent the evolution. So we have the zinc SOS, the zinc SoC on the left side, and then the MP SoC, which is the multiprocessor system on chip on the right side. And on the left, like the zinc just like combines a dual a Cortex A9 processor with a programmable logic on a single chip. So instead of just having like a separate processor, you can like combine it with the PL, which is the FPGA itself. So that's the one like in the yellow. Then on the MP SoC side, which is on the right side, it's like you also have like two like a processor like cluster. So we have the processing system and then the PL as well. And then aside that, we also don't have only that, but then you have the real-time processing unit for like real-time simulation. So like maybe if you want to like control a motor or your like devices, you can just connect. And then we also have the application processing units where you run your like a application. So this some of these applications can be like your ROS, or like it can be any project that you have in mind that you would want to run. You will go through them in some of the applications. So we need to also understand some of the building blocks of an FPGA, since it is just like the fundamental parts. So we will just zoom out and see like the big picture. So at the most like fundamental level, an FPGA fabric, and if I say an FPGA fabric, it's just like basically the like these three components. So the lookup table, the D flip-flop, and then the multiplexers. So first, the lookup table is which you can like basically configure to implement any like small logics. So you want to like so you can like simply change the values stored in those like truth tables. So you can just like think of it as like a tiny like programmable truth like table. So you can just change the input and then you will just find the answer on the output. We also have the D flip-flop, which gives your circuit like a memory. So they hold a single state and from one clock to like the other cycle. So it also adds some kind of like flexibility, and it can also be used like for like counters or also like a state machine, or you can also have like a pipeline from there. So the next one is just the multiplexers, which is also like very important. So you can use the multiplexers to also route your signals and then also like select like between different states or like different logic paths. So this is what gives the fabric the flexibility like to use. So all those three comes together to form what we call this the CLB, which is the configurable logic block. So it is more or less like a repeating tile. So you'll find tens of thousands inside a chip, and I will show you that in our uh, like in our next line of a presentation. So like beyond the CLBs, we like also have some kind of advanced like hardened blocks. So these ones can just be the DSPs, the digital signal processings. So they are normally used for fast like processing like arithmetic operations or for math operations. Then we also have the BRAM. Uh, okay, we also have the BRAM, which is also for it's more or less for like a on-chip memory. And then the hard IPs as well, just like a PCIe's. So they more or less help with like communication and also for fast transfer of data. So this is the actual basic block of a CLB. So as I mentioned, it has two inputs, or sorry, it has like a four input. So based on your configuration or based on what you would want to achieve at the output, you can um, like configure your logics at the input, and then this flip-flop just gives your circuit a memory, and then you can like either bypass the flip-flop or you can also pass through this. Then you have your AI, like your output. So this is like a pure logic, which we normally um, like implement in an FPGA, like a fabric. So this diagram also shows, so like maybe where do you even start from if you want to like run a FPGA program? So you first start with with your Verilog, which is your code. So you can have your code either in the like Vivado platform, or you can also have it in the um like with your like normal VS Code. So you can like describe your logic based on what you are looking at or what you want to like achieve. So like, let's say if you want to build like a simple block IP, you write your code in either one of these two languages, then you describe the logic, you synthesize it, and once it is being like synthesized, it generates a gate level like design called a netlist, and those netlists can actually be compiled onto the FPGA. And once it is being compiled, it generates what we call a bitstream. So the bitstream is your actual like hardware, which you like download to your FPGA boards. So we move forward to like talk about how to design an FPGA application, because what I've actually been saying is just like the fundamentals. So we just have to see like what it actually does. So we see like the beauty of a FPGA. So this is on the left side, this is the board that I normally use. It is a it's a pink um, ZU3, which I got from Xilinx. So we did the programming like in Vivado, which is the platform. So it is a 2022 on a Vivado. Then I built like a block design. So the block design is more or less like, like I built a block IP. So I just wanted to blink a LED, because if you pick any like complex board which you don't know anything about, you would first want to start from the like the basics before you build up on whatever that you want to achieve, or you would just want to have control of the board. So here I just built like an IP, and then I packaged that IP in my Vivado. Then because it's just like a like an like an LED blink, so it's it's just like a custom LED IP core, so which can be used for blink, and it is we like later exported it into the Vivado, and you can, once you just want to blink an LED, you can just call it into your Vivado platform, and then you can just use it. So I also connected an Axie GPIO like peripheral to it, which we would want to use for our Petalinux, because you wouldn't want your like program to just sit on the hardware side, but then you would also want to like control it from the from the PS. So with the PS, you can be able to have advanced control of the LED. So we also have some kind of Axie interconnect, which we use for like communication between the two blocks, which is the PS and then the PL. And then we just set an LED output, which we will see from the blink here. Okay. Okay. If you can take a look at it, it's supposed to be a video, but for some reason it's not playing. But then the two LEDs on the bottom part of the switches, you can see one was for the Axie GPIO pin, and then one we blink it from the PL side. So which is the bit stream that we generated. So the other one was just for the Petalinux, or from the processing system. So I use the two like communication protocols. So from that, I exported the SSA file, which include a bit stream. So the SSA file is after you have built your bit stream, it generates the actual hardware file. So you can basically use it or like export into your Petalinux. So Petalinux is also like a platform. So if you want to use your or blink your LED from the PS side, instead of like using a bare metal application, you can use a Petalinux to like be able to control your LEDs. And this is how we actually have our like normal microcontroller boards, like like an Arduino, and then other boards like the ESP32s. Like this is how they have been wired. So you configure them by your own. So on the Petalinux side, you can create a project. Then after creating the project, you can like basically configure it, and then you build a package, because it's a kind of, and those kind of needs some kind of like essential components to be able to work. So we also have like a runtime, like the buses. So after you generate your um, after the SSA file, it assigns like the bus of your Axie GPIO, so you know the particular uh, like GPIO that you are actually like referencing. And there's also a constraint file which is being linked to your GPIO pin as well. So all those ones are being defined in your code. Okay. Okay, so let me know if anybody have any question or if I should like continue before I talk about the next like project. Okay, Chidozie.
Yeah, I wanted to ask a question, but it has been a good introduction and good overview of FPGA operation. But
Okay.
if you could go back to your last slide, the previous slide, no, the previous one, back.
Mhm.
So your step theory, when you said runtime and AUP, when you said Cortex A53, I just want to make sure, I just want to confirm if that is a chip, additional chip on the side, like a microcontroller on the side, is that attached to the FPGA board, or that is kind of embedded into the FPGA board, or it's an external chip?
Okay, so if you can see the chip right here with the yellow
Yeah.
and black, so there's the heat sink on top of the chip. So like just to be able to like preserve the heat, like dissipation. So this is an MP SoC. We have an SoC just like the Zinc 7000 series. So those ones are just like a normal SoC, but then with the MP SoCs, we have quite a variety of like applications. So we have like the RPU, which I think I talked about it here. But then they are all embedded on the same chip. It's not separate from it's not separate.
So in that so in
So
that
that's
case, this is more like is this external chip embedded board, embedded FPGA board?
yes. So on my right side, the project that I implemented, I just did it on the MP SoC on this one. But then it can also be done on this particular chip, which is the SoC. But it all depends on how you like create your block design. So your block design, you need to know the particular chip that you are using, which is based on the particular board that you currently have.
That makes sense. Thank you.
Okay. So just to throw more light, you can just look at ping ZU and then ping ZU3. You will see the differences between them. Okay.
Thank you.
All right. Okay, so this is the second project, which I had the like privilege of working on. So it is an OpsLAM. So an OpsLAM is an like a oriented fast and then rotated brief. So it's a part of SLAM network or like SLAM or like framework because we have a VSLAM and then which uses like just the camera and then like the normal SLAM which uses just the LiDAR and then the for your like navigation. So an OpsLAM also uses a camera, but then this time around it comes with a depth sensing camera. But I didn't have a depth sensing camera like in this case, but then I just wanted to run some few inferences on some images and see the performance of the FPGA. So it is more or less like a real-time system camera, which we can use to. So when a robot like get to like a particular location, you would want to like the robot should be able to know where it has gotten to or know its particular environment. So an upslam is just to help a robot to like navigate its surrounding and then know the particular like position where it is like in a particular building. So it doesn't do any it doesn't have any network with a GPS. So it just uses like a dense camera. So with a dense camera or with a depth estimation camera, it will be able to like capture the surrounding and then be able to know where it is in a particular area. So it's very important in the computer vision because like in a real-time autonomous system, like drones and then self-driving, they need to know where they are and then where they are being like headed to. So this is like a block design, but then it's more detailed because it combines an accelerator, which I actually this is a repo that was built. So what I did was to like port it to it was built with a ping Z2 board, so I ported it to a ping Z23 just to like compare the like the performances that the two of them have because like definitely a ping Z23 um would have a lot of like lookup tables or like deep or like DSPs which will like overshadow a ping Z2. So this is like an up feature, like an algorithm which was done. So it finds the distinct like point in an image, and then it just creates like a compact like fingerprints for the for like each one. So the image just splits. So from here, you just feed in the image from here, and then it's split into a two like parallel path. So one smoothens is which is the Gaussian blur, and then the other runs a fast, and then like just to find the corners, and then ranks them, and then like compute them with like based on their orientation. So both paths meet here, which is the like which is the descriptor. So it just like you just find the key features like in a particular image. So on my left side, what is being um, like implemented here was the same thing that was done on the left side. But then this was like in a block design because you would want to run on like you just want like performance and then also just to make it fast. So we package this into a block IP. So these 4 blocks can be packaged into a single, like a single IP. But then for this case, I only used it because I just wanted to understand the actual algorithm and then also just be able to expand and see what is like inside the code. So from here, we need to feed it into our Zinc like processing system, which is this. So we have like the 3 accelerators, which is the fast, the Gaussian, and then the brief descriptor. So they all like kind of like generate a binary descriptor. So those binary descriptor is what forms the like the key point. So what connect them is the AXI14 stream, which is like a bus or like an interconnect. So instead of just like storing those like intermediate results like in a memory, it just like read them back just like the way a CPU would do. So it just like read them back, and then in each block it passes like the data directly to like the next stream because we have. So if you look through it, I don't know how you can see, but then if you look through it, each of them have their entire DMAs as well, which we'll talk about. So the one piece that I want to also point is like is the DMA. So the DMA is like the direct like memory access. So the ARM processor on the PS side needs to get the like the image into the PL and then like gets the result also back out as well. So like without stalling itself or like without doing it manually. So the DMA is just like basically used to handle like the data transfer between the PL and then the PS. So the image just shows like the DDR like memory as well. So the processor just simply transfer, which we have it here. So it just like simply transfer to and from the points of the DMA into the accelerators, like the three accelerators that we have here. And these three accelerators come together into the, sorry, this, like the three DMAs come together into the Smart Connect. So the Smart Connect has a very high bandwidth, which we use to like connect to the zinc chip. So this is the zinc chip, the MPSoC zinc. So we also, I did some kind of comparison on how like the performance is being achieved on the PingZ23 board. So on the CPU side, we can see we had a very small like performance in terms of the frame per second. Then I compared it to the PingZ2 because that was the benchmark. Then on the Z23, we had like 72 frames per second. On the ZU, it was just like 56. And we can just Google it and see the performance of the PingZ23 because it's just like a repo. So on the resource utilization as well, we can also compare and then like look at the lookup tables because they are very important. For for like Z23, we like utilize a very small like amount of lookup tables and like compared to the ZU. So it was just like a decrease as compared. And then if you look at the other like resources, we also had a very good amount of performance. So this also shows the actual key frame or the key point in the image. So it's more or less like how the camera sees sharp corners inside an image. So you can see these are more or less like keyframes or like key points. And that's how an upslam like actually operates. So this is also the CLBs. So as you can see, we have quite a number of like configurable chip. So this is more or less like the fabric. So, after the bitstream it just generates this as well. And on the right side is just the power on chip. So we can be able to like measure the amount of power that the board is actually utilizing. Okay, so for the second one, this is also a LiDAR pipeline, which I'm currently working on as a project. It's not fully done, but then I just wanted to throw a picture on some of the applications that you can use and an FPGA for. So I have my like the LiDAR. So I'm currently using a Levox Mate 360S. So it is a very powerful LiDAR, and the connection is just like a 12 volts. You can just like connect with a 12 volt adapter, and then it just have your Ethernet port for data transfer. So with the hardware side, I'm just like linking it to this. Like I'm setting it up like this. It has its own like viewer that you can download and then look how it looks like. Then we would also want to do some kind of edge processing as well, because it is very important to transfer your data right from the PS, sorry, right from the PS side to the PL, because you want to transfer your data or like your binaries like in a very fast pace. And all these, you cannot do it without using like a ROS, which we normally use for the publication and then the subscription. So you can on the last end, you can also do some kind of obstacle maps and as well, because we want to do and like build an autonomous system. So based on the view from the environment, the robots will be able to like navigate. So it's all based on like decision making, because you like robot needs to make a very quick decision, or even like a autonomous or like vehicles need to make a very quick decision. So you wouldn't want to like miss the little bit of time. So data needs to be like transferred in a very fast pace. So the first one is just the LiDAR view of how the levels 360 view looks like. And then yeah. Then so this is just like the capture of how the LiDAR looks like. Then I'll just run through some of the applications which I'm currently exploring. So it has a very wide application as well, which needs to be worked on. So some of the uh, like modern FPGAs applications, so it can be used in an HFT. So HFTs are like a high frequency trading. So sometimes the decision making needs to be like very quick. So the time interval between when a news or like a message is being said and how it reacts like in the market is all based on like fast processing of data. So you can apply FPGAs in this because we want like a very high performance. So the next one is also performance. So as I mentioned, we had a very good amount of like resource utilization in the project that I shared because we had like a very high frame per second in the upslam. Then we can also like consume quite significant less power because in edge computing or like in edge deployment where battery life and then like thermal constraints matters, you would want to use a little like power as you can. So some of the applications as well can also be used in an NLPs, which is the natural language processing in computer vision. So you can also do object detections as well as speech recognition, medical devices, and even in the network space as well. You can also use that. In AI acceleration, you can reconfigure your neural engines for an adaptive like power efficiency references. It's so in deep use applications as well. So you can combine like Vitis AI, which is a very powerful tool, with like a DPU overlay or with a DPU IP. You can easily build like a simple like train your own model, like deploy it, and then also like deploy it on the PL side because you wouldn't want your like application to just sit on the PS because it moves like very fast like in the PL. So in autonomous vehicles, as I mentioned, and also V2X application. So ITS edge processing is very important because once you have your LiDAR like in a particular intersection, you'd want to like process information like very fast. So that you'll be able to make like decisions. So in edge, like in V2S communication, you have like a pedestrian on the road, and then your like LiDAR like in a particular intersection, and with the roadside unit, you'll be able to like communicate between the two of them. So these are some few references in the presentation, and thank you very much for having me. I have my projects in Hackstar.io. If you don't like understand some of them, you can just like go back there and then like read, and then also my LinkedIn profile as well. Thank you very much.
Awesome presentation, Clark. Awesome presentation. Um, I guess I'll say any questions. I have a few questions myself. Nothing too crazy, but I'll ask others to ask their questions first before I dive in. But a good presentation, definitely. Thank you
Thank
so
you.
much, Clark.
Thank you.
Yeah. Guys, so the floor is open. If you have a question, just show a sign, thumbs up, raise your hand, whatsoever, and then you can unmute yourself and then go ahead with it. All right. You mentioned, if you go back maybe a slide or two, you mentioned V2X and but you did not explain, for the sake of the audience, what V2X
Okay.
is and what is ITS and so on. Yeah.
Okay, so V2X is vehicle to everything. So the X in the V2 is, it can be a pedestrian, it can be a vehicle, it can be like a roadside unit. So a roadside unit is just like a device being mounted at the intersection. So it's like communicate with either an onboard unit. So an onboard unit is also like another term, but then we use a roadside unit to like communicate to an onboard unit, and then the onboard unit will transmit some of the basic safety messages that it receives from the intersection to either your tablet, or like it just broadcasts the messages to your tablet. So, and ITS is just intelligent transportation system, and is very common here in the US because you want to um, make like our road quite easier to like navigate around. So it's just a way to improve our transportation system on the road.
All right. Thank you so much. Any more questions?
Maybe just a basic question.
Okay.
Again, thank you for your presentation, Clark.
All
So
right.
if I want to work on an embedded project and I have both the choice of a microcontroller and an FPGA, what should guide my decision making as to whether to use a microcontroller or an FPGA?
Okay, so there are quite some projects that can be uh, like implemented on the two of them. But sometimes if you are looking for like performance, or you are just looking for something that is low cost, so you wouldn't want to spend so much on an FPGA because it depends on what you want to like achieve at the end. So a microcontroller is just like an ASIC. So an ASIC in the sense that once it is being taped out, you cannot like change the like the configuration or the hardware configuration. So if I want to have something that I can have control on, I go in for a FPGA. If you just want like just a simple microcontroller which you think it can just perform this particular thing, like this one thing, then you just go in for like a microcontroller. Okay, so I don't know if I answered your question, but most of the time you just would want to go in for um like either one of them based on what you want to achieve at the end.
Okay, thank you.
All right.
Clark, I would
Okay,
like
so
to.
follow,
Oh, sorry.
so
Go on.
following up on Obed's question, so like for commercial, so for companies who have so much money like Tesla and Waymo, do they use the FPGA routes like for their autonomous vehicles?
Okay, so it depends on where they are applying, or like at the point where it is being needed. I haven't actually gone deeper into the autonomous side of Tesla, but then I know for edge computing, if it is not an FPGA somewhere, it will probably be a chip, which is similar to an FPGA, which they normally have like control uh, it might not actually be, it might not be like an FPGA, like a whole FPGA, or like a like evaluation board, but then it can just be like a particular chip which has been like assigned or being programmed like an ASIC for like that particular like a autonomous system.
Like maybe to add to what you said in answering Hack's question. So generally, the best hardware platform for your model in terms of efficiency and speed is the hardware that is built for that particular model. So if you look at Tesla, it built its own chips, but that costs a lot of money. Not everyone is able to afford it. There are just a few companies who do that. So generally, when most autonomous or companies that build autonomous vehicles start off, they usually seek partnership with OEMs, which is car manufacturers, and then they look for tier one suppliers. So that way, what they do, what happens is that they take, let's say, a company that already has a platform that does the intelligence. It could be an FPGA, yes. It could also be an NVIDIA. It could be Mobileye. It could be any platform whatsoever. And then they try to establish partnership with the OEM and see how they can define a model that suits the OEM's requirements and then run it on that particular platform. Sometimes what they do is that they'll do some sort of benchmarking with their specific model on various hardware platforms to see the one that has the best, performance, and then they will go on with it. But to answer your question, an FPGA is useful in this scenario of autonomous vehicles, especially the electronic control unit part, to gain some influence in architecture and influence and knowledge in architecture, because an NVIDIA or Mobileye or any of these other platforms, Qualcomm, does not give you that knowledge or insight that you can get from an FPGA by going down to the nitty-gritty, playing around with your own peripherals, the accelerator, etc. You don't get that in all these other platforms. Yeah, good question, Hak.
Okay, so just one more thing. So for the HFTs too, like they also have a lot of money, like especially the big ones. So is there a reason for using FPGAs like to test out different stuff to like try to get the most performance? Because you earlier you said that for most of the time, your best solution is like a chip built for that solution specifically.
So, Clark, do you want to, or do you want, do you mind if I?
So it's for HFTs, it's more boils down to like decision. So I don't know if you have been in trading before, like in a particular news like section, because like the clock tick or like a week, like just take a particular second to move up and down. So I mean, I'm yet to like have a particular project to know how a HFTs or like have on how to use like an FPGAs in HFTs, but then I know it's all based on the frequency. Yeah, so like the frequency, the time interval for the like message to be converted into like a particular signal. That's that's where the FPGA comes in.
Yeah.
Yeah.
Right. So thanks, Clark. So when it comes to HFTs as well, you have the flexibility to really thin down specific blocks especially if you, as example, if you say Ethernet, because usually the packets are sent in Ethernet, right? The custom or the standard Ethernet IP is bulky and is built for generic purposes because you have clients that are in automotive that are doing other things, right? Now, some of the things that the IP would have to do would require to spend more time on processing the data. So this will induce more latency, right? So what why FPGA is useful in HFT is that it gives you the flexibility to go and build a custom-made solution for you that only has the component that you need. Small, efficient, less resources, and high speed. So in the end, even though it's a normal TCP/IP stack, you would end up being more efficient than the general to other products on the market. I hope I'm able to answer your question.
Yes.
Right. So thank you so much for the time. Unfortunately, we have just 3 more minutes. So if there's a question, please feel free to ask one last question, and then we will have to say our goodbyes.
Hello.
Hi, Prince.
Yes. So my question is, beside these two industries you've mentioned, do you know any specific industries or like specific companies that have a special use for an FPGA?
Did you say industry?
Like an industry or a specific company which has had a specific use case for an FPGA in their workflow?
In their work, okay, I know Phoenix have been using it for like objects and post estimations. So like post estimations is more or less like you just want to estimate the posture of a human being, like in a particular, either it can be like in a workspace or it can be like in a particular area. So you can check a Phoenix. A Phoenix is one of them. Also microchip. So in my last conference, I saw like microchip also used FPGAs as well for facial recognition as well. So that was, so I'm just saying the ones that I've actually seen. So like microchip is one of them. Affinis is one of them. Otera, I don't know if you know Otera. So Otera also is with Intel. So they also use like they apply it in like robotics for like robotic automations. So you can just look on the net. You'll be able to find like these companies. Like just Google them.
Prince, is your question answered? Did he get it right, or were you asking about other? Could you ask your question again?
So my question was, besides the two use cases you mentioned, automation and HFT, I wanted to know more industries, more companies which have had specific use cases for FPGAs in their work
In
or
their
their
work,
or their products, anything.
So if I understood correctly, Clark, I think what he's saying is you mentioned HFT, you mentioned automotive, and he's asking if there are other known companies that uses FPGA, right?
Yes.
yes. So the company that that uses it, or like some of the use cases of an FPGA, I just want to get it right.
Yes, that's the question I asked. I think you've answered it. When you mentioned microchip and Altera
Okay.
too.
Okay.
Yeah, I think to answer what, sorry to throw more light in there, but just like what Clark said, because I think FPGA is more like a normal chip, just that for you to go through the process of, you know, creating your own chip and taking it out could take about a year or two and involve a lot of money. So most companies, instead of to do that, they can reconfigure an FPGA to do what a chip would do for them. So not banking on a standalone chip. So mostly in the United States, right here. I know the aerospace, they use microchip very well. Also in the Medicare, as long as anywhere they could use chip, any manufacturing industry, any place where they do high precision, high throughput, I think FPGA is very important in those areas. So any areas where you think someone could design a chip or implement a chip in your system, your computer, or whatever, because you can run a processor on FPGA as well. So I think it depends on your own use case. Any industry could use it, but it now depends on the application on the industry.
Thank you very much, Desi.
I think there's a question in the chat from Kene. He asked, can all FPGAs accelerate AI tasks?
Yes, most of them can do a acceleration, but it all depends on your number of lookup tables. So, and just as I mentioned, so the number of DSPs and the lookup tables exponentially increases with the cost. So based on the kind of task that you would want to achieve, you're going for like the right board. But then most of them can accelerate AI tasks, but then it depends on the like kind of project that you would want to do, or the like the chip itself. So first I would say it should have like some kind of advanced like both the PS and then the PL. So because you'd want to offload some of the high computing like computing task from the PS to the PL.
Right. Okay. Thank you so much, Clark. I think that was our last question. And yes, thank you everyone for the questions. And I hope you had a good time. And we look forward to welcoming you in our next